what we will be looking today is about artificial neural networks. So artificial neural networks was developed considering the same as of your brain, right? How the brain works. Based on that thing has been taken into account, and then it's totally inspired by a neuron, the way brain works, right? So the key work in this process is like processing the information. So the main unit of your brain is neurons, which is this one. These passes the information from one neuron to another neuron, and this area is your decision making, like how much to remember, how much to forget, and all those things, and what things new information to be passed. Once that is done, processing, it passes to the axon, and then it passes on to the next layers, or you can say next neurons nearby, so that all things goes like this. All right. So as people mimic and say, human like in human, women's brain work very faster as compared to men brain, right? The way the signals proceed from here and there, it is very fast in women's as compared to men. The thing is, it totally depends on the way computations take place or the decisions are taking place at this point, and the signals will be passed to the next layers. Similarly, you have architecture for our artificial neural network, right? Um, what actually artificial neural network was? It was like, let's say, three different whys for why and who were involved, and what is actually the component of AI, right? So Franklin Roosevelt in 1958 was the one who was the author for artificial neural nets, and he did all this research and tried to mimic the human brain, right? And build a model or a machine learning. The components for the ANN is the perceptron, the independent neuron, weights associated with that, the importance. Actually, weight signifies the importance of each parameter, right? Let's say you have a lot of parameters in it. What is the weight associated with that? What weightage it consists? So that is very important. Ultimately, in the neural nets, what you learn is which is weight associated with each input parameter. Biases to control the error factor there, the unknown error factor. Activation function at, at each neuron, what makes this to be activated, what makes it to be inactive, like that, right? Those things. The outcome and back propagation is another concepts there. So we will be looking today in these areas, right? Let's say what actually a single perceptron or a neuron does. Neuron is a biological term for a given single basic unit of your brain. Right? Perceptron is a mathematical representation of your neuron. Right? That's where I called it as perceptron, or you can call it as a neuron also. That's not terminology differences there. So you have a mathematical representation of all this. You say perceptron or a neuron, or people call it as node or unit. It depends. It depends. Right? You all three or four points to the same thing. So neuron is the basic unit of the computation in neural net. Right? Um, it often called as node, unit, or perceptron. So there are a lot of input for that. Let's say these are the input areas. I'll just pull out those. Yeah. So if you see here from here, so if you see this, from this I get x1, from this I may get x2, from this I may get x3, right? This is how I feed my input values. All right. So this is how, if you consider this one as your neuron, is what your this area. What you're doing is you're providing them the input values as x1, x2, and so on, x3, 4, 5, xn. These are the input parameters for you, which are associated with some weights. Weightage in the sense this has some weightage. This has some weightage of factor weight 2. This has some weightage factor with 3. And this has a weightage factor of W of n. Right? Each contributes to a function and gets their associated input as well as their weights. How significantly this input value is. Right? Those things are there. And with some constant value are to maintain the error factor and all those things. This gives you your y value, what should go for the next actually. Okay, that is what is being represented here, the real format of a neuron, right? So if you see, it is a function of these stuff which consists of weight and input as well as weight, and then biases. Okay, this is one important stuff we need to remember as of neuron, what actually it consists of. Each neuron will give you a y value taking various input factor and the weight and biases. Some point you get biases from here, whatever. It's real time. If you want to just analyze, it will be like this. And the other stuffs are like in the neuron, it happens like this. If you see the data in the real time, it can be of two different varieties of the data. Data can be a linear format. For example, linear in the sense, probably you might have learned in linear algebra, mx plus c, right? This was the slope function for linear stuff. If I start with 0, x as 0, right, it will be a constant value. Probably it will be like, if it is starting here, then graph would go like this. If c value is somewhere around -5 something, right, -5 or so. So at that point of time, your constant would be here. And then m value is your slope factor, and x is your coordinate, x time, how it goes and all this. Actually, yeah, the graph would start something like this. So here your x factor is, c factor is, in this blue line, your c factor is -8, like that. Okay. So just for a reference, I've just given that. Probably can just count those. Yeah. So linear, for an example, what I'll give a real-time example for this, right? What happens is you're trying to get a loan, right? This is your data set, loan prediction stuff. Okay. What we are trying to see is, this is your y value, which says decision to be taken care based on the loan. This is your probably name or so, whatever the values. Okay, name and okay, name, then age, then your salary, then your spouse working status, then your credit card. Based on that, you are taking decision either to give loan or to not to give, right? This is your binary class classification problem. Okay, your salary, age, and all those things made some impact on it. So you will end up with a function which says, if your name, you can drop it, or something like that, you can drop it. Age, associated with that some significance, saying that age would give, among the loan to be given as your 100% weightage, you say age would uh, implies you with a 20%, right? 20% chances, weightage of loan. Then point 0.1, 30% chances of 30% chances, weightage of your salary. Shit. right? Salary plus somewhere around your spouse working would be like 10% to give your loan status. Each has some weights associated with that, and you don't have non-linearity in this. You make a equation such like mx1 plus x2 into m2 like that, right? M2 plus x3 m3 and so forth and so on. This made you a equation simple linear regression problem. Got it? It creates a simple linear regression. But when it this forms a linear data. This forms a linear data. But sometimes there will not be a linearity in the data. It can be like non-linear data. It can have any other patterns in it. That particular data, those particular data can be considered as your non-linear. So probably you cannot find the significance when you try to segregate between loan giver or non-loan giver. You cannot segregate them. This class you cannot segregate um, by this linearity differentiating. If you provide this line, those who are coming above, you can give loan. Those who are coming below this, you cannot give loan. Sort of like classified. But in this case, you are it will be like parabola or something else or something else. That point of time, you need to learn the data in a different way. So in ML, you have a lot of other algorithm for handling this log, exponential and all those things you use in order to make this one to a linear form first. You make the exponential factor and then log likelihood you use that, right? Log likelihood, you use those and then you make this transform this into a linear format, and then you apply linear regression also, so that it will be like fitting this equation, or else you provide this nonlinearity understanding using some of the functions available there, or neural nets understands that because of the activation function. The main intention of introducing you with linear and non-linearity data is to understand the trends of the data available there, first of all, and how neural networks tackles this linear and non-linear data. Okay, it learns based on the quadratic functions here. So here it is like simple. You have a squared here so that the graph would look like different. You don't have a slope factor. If you have that, it is like slope of a parabola or something like that. You have a particular function for it. Similarly, neural nets understand each data. Either it can be a linear or non-linear using activation functions. Activation functions are the one which we will be looking here. Based on because of this, you will be able to tackle both linear and non-linear data. Okay, that is where most important thing people will ask in an interview, that saying neural net how it handles linear and non-linear data. You can say that using activation function. How it does that, we will look in when we go here. This is your non-linear data. This is your linear data. Got it? This is your non-linearity. It tackles both. When it comes to the activation function, because of this reason, this region, I mean this reason for that, it handles both activation, linear and non-linear data. Okay, just remember the one thing: linear neural nets handles both linear and non-linear data using because of the activation function. That's all. Going further ahead, one of the important aspect is understanding the architecture of a feed-forward network or simple neural network. What actually is your feed for a simple neural network consists of, right? It's the input value and the output value. This is all your inside your box, which takes as your simple neural network, right? What happens is, as we saw earlier, each input value is associated with its weight in order to pass on to the next level. This is your next layer, right? This is the input layer. This is your middle layer or hidden layer, right? Where the summation of all input takers, weight one, weight two, two of two will come here, right? Weight two of two will come here, and then this also goes into this one. Weight three of one actually. So what happens is three of one, two of one, and yeah, so weight are associated with each values will come here. Okay, so at this point what we are doing is we are passing each input to a perceptron. This is a perceptron and the weights associated with that, and each perceptron will have some activation function. Okay, each perceptron will have an activation function. At this point you do summation of all weights and their input value, which is this formula, if you remember that, which is this formula, weights and input value with the bias is your single perceptron. This is your single perceptron. Similarly, your single perceptron consists of summation of all those whichever are coming, whichever are the input involved. Right? At this point, it comes here, and then at this point you do activation, use activation function. Based on that, remember this one, we do activation function. Based on that, output goes, y values goes to the next layer. So similarly this value goes to the next layer here, which has another activation function and then provides you the output. This is the architecture. So I'll just put on the equation for this one, this perceptron called A1, right? uh, A1 of 2 is equals to function of whatever x naught into weight 1 plus x1 weight because it is starting with 0 and going to the first one. Uh, 0 and 1, 1 and 1 plus x2 weight of 2 comma 2 comma 2 plus x3 weight 3 plus biases would be the entire function for just this one. See the computation complexity of each layer, right? If you see the computation complexity of each layer, you find that this computation has to be taken care at each perceptron to get this. And then on top of it, you apply either your sigmoid activation function or ReLU or something like that, which we will see here. So just that on one perceptron, this computation will happen. And this information would be passed to the next layer. For nonlinear data, for an example, what we can look for is probably I'll give you a better example when I go through online. Because sometimes what happens is, so sometimes you cannot directly get the classification done. So, and for nonlinear, sometimes what happens is you cannot make a classification between those two different sort of classes. This is one class, this is another class. This is your linear example. Nonlinear, what will happen is you cannot directly segregate like this. You need to put in into another dimensional factor. This is 2D, right? This is two dimensional. Sometimes what you need to do, you have data in this format. What you do in order to classify that, you put in another. This is in the three dimensional. You have something like dimension. I'm bad at drawing. This is your X, Y, and Z. Probably this. What you're doing is you have a um, this parabola. At that point, what you can do is you can do the classification by just putting another line. Whichever is below this area is onto giving a loan. This cannot be given to a loan because this segregate that. The line this segregate that. So sometimes problem will be like totally different where you have lot of, let's say, uh, miles per gallon, and yeah, one example where you can see the direct dependency between two stuff, which is speed speed of the car and displacement. So you are at a 5 miles per gallon, and you suddenly, I mean, sorry, 5 kilometers per mile. Sorry about that. And you suddenly put on your brakes. So it would take a displacement of probably like 6 miles, not just 6 meters, whatsoever, right? The unit would be whatsoever. So at this point, it got a displacement. This is your displacement. At this point, it got your displacement. Next to the same thing, next what happens is you got your value. You got your at 10 miles, you stopped by somewhere here. Earlier you stopped here, and this was the one. Okay. So you got something like this linear example as you go further, right? Something like this. This is your, so this is your linear data actually, linear segregation, where you trying to predict the value, and it gives you a linear problem saying that at 40 miles per gallon what would be the value, so that you predict the y value that you'll stop by this much distance. This is your linear example, simple linear example. But when it comes to a complex problems where you are trying to do, where you get a lot of other parameters and your data would be somewhere something like this. It will not be always a prediction will not be like this. Data will be somewhere, it starts something like this, and then linearity is not there, which is called as nonlinear data. When you plot across increasing x value, y, how trends would goes off is it non-linearly move here and there. That is what your non-linear data. In understanding, I would quote a better example taking help for online, and then I'll let you know. That's where you cannot do a segregation for that. So you put in onto another dimensional, so that it makes you a better understanding for it. Okay. Yeah, that pretty much thing. This is what it gives, the weightage of these values, and then to that of biases would be there, and then activation function would be imposed on it. Then it goes to a next level. Okay, that's how you get the y value. So we will look in here. So forward propagation, what happens is the one value, let's say here input one is active, it moves on, here, you get another activation, and based on that it will say that either it was 1, 2, or whatever. It was like multi-class classification. The outcome here in this scenario is 1. Based on that you say either 0 or 1, whatever. Here also you have two outcomes like that, which can be saying that this is one class, this is one class, sort of something. So this is how you can understand that given an input here, one layer of hidden activation functions, neurons and all those things, which learns the pattern, cumulative, all this. This is a cumulative of all, right? It can be this will also be linked, because just to make simple thing, it is not linked it, and then it grows from there. This is called as a forward propagation. Given that one, it comes here, weights are being updated here, and then it goes to the next level, and the values is being available here. So next, what is there is at these point, at these values, what is the activation function we use? Either you use sigmoid, either you use uh, TANH or ZELU, which is very famous now, or TANH. What are the various other stuff we will look in here? Based on that, it will activate your function, right? Accumulating all these things, you get some value, and some threshold will be there. Above that, it will be 1 or 0, whatever, it pass on to the next.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.